challenge was with, as well related to the standardization of data. We decided to have an approach that is mostly based on ontology, and ontology as a concept comes from philosophy. It's like a matter of existence, of being, and if something exists and is the same thing, we have to standardize it. So what was the main problem that we stated even in the evaluation phase was that most of the buildings account for 30% of the energy consumption and electricity demand worldwide. And improving this, the efficiency of how the energy is used can reduce the cost, but can also lower the carbon emissions. But there is a lack of how the data is used and how it's named and how it's standardized. So this causes that the systems are not interoperable between each other. And if we consider there are a lot of buildings and all of them made from different engineers, I mean for the energy systems that are made from different engineers, and they use unique systems and they use different technologies, so it causes chaos on how you can make analysis and our offer optimizations to them, because there will not be a model that fits them all. So we also had a look on possible literature review. We had a look on as well on the industry to see if there are public examples on similar usages or efforts for standardization, but we couldn't find any public data set that did related work. However, we did find a few articles on other researchers that tried to implement ontologies and build a standardized model for how the energy data can be managed. And we will have a look later on this an overview of how these different ontologies work and why we chose what we chose for the rest of it. As well, we had a look on international standards, and the most famous international standard is ISO 50001 on energy management system. However, this standards focuses more on energy policies and targets that the industry should have. So, for example, when you build like a heating system, what are the policies that impact on it, and what are the targets that they should try to implement for the system to be energy efficient, but as well to lower the carbon emissions. And why do we need the standardization? Because of the data inconsistency across the building, as you mentioned, and as well because there is differences of how specific engineers will make their system to others, and this will lead to inconsistencies. And there is difficulty in defining key contributors in the energy efficiency. And in our use case, what it was given, it was the data from the municipalities of Silesia for the schools and how their energy consumption and the heating system. And they use some Excel sheets. And however, there is not a defined standard of identifying these key components that impact on the heating system. So as a first step, we started with analyzing what we had that Patricia will present now.
One of our main objectives was to find the publicly available data sets that we could find about the heating management across Sweden. After extensive research, we could not find any publicly available data set except for one that had very granular energy data in Sweden, which can be seen in the two tables provided, and usually the information is just more general about either district heating or just general electricity consumption and prices. Then we could also find meteorological and geospatial data, but there was not much to map it to. However, we were given a data set with 52 with 55 buildings around Skellefteå, mainly school buildings, which we then used to obtain insights by performing data analysis. The dataset consisted of multiple features such as energy classes, energy consumption, and building-specific attributes like heating sources and property dimensions. But it also had a lot of data that was not necessary for our use case and for establishing the heating consumption. So that had to be removed during preprocessing. We then obtained through simple analysis a few graphs, as for example a distribution graph of the energy classes, which revealed an imbalance in the class representations. But we, as the dataset was quite small, we couldn't quite understand which were the factors that were causing it, because the data was quite spread. We also obtained a correlation matrix, which presented strong relations between a few factors that were predicted to correlate. For example, the total energy and the district heating, or just the heating. But we also found a relation between the energy consumption and the building area, which can be seen here. Then we tried to perform some machine learning operations on the dataset. We tried logistic regression, decision trees, naive Bayes, and random forests. But as the dataset was quite small and we had a lot of rows that were half empty, even with cleaning, balancing, scaling, and feature engineering, we could not obtain good results. However, we managed an accuracy of 62 and F1 score of 60 by using logistic regression.
Now, our solution for how to standardize the data. And so, to put it simply, our solution consisted in two things: the data visualization we just detailed, and how to put this information into use. So we have all the data and we have seen it and we have done all the data analysis possible on it. But then the question of how can we represent this data to be the most conform or to fit some model. So we came up with this solution. It's a common data model that can enable data interoperability between the building internal and external sources. So basically, what we want is that we can put the data provided by any municipality. In our use case for the municipality of Skellefteå, and we wanted to put everything in one model that will fit all. How we did that? It's by brick schema. Like we detailed yesterday, it presents an integrated cross-vendor representation of the multitude of subsystems in modern buildings. So you have the BMS, the HAVC, the lighting, the security, sensor data, and all the data that is around buildings. Now, it reduces the reliance upon the non-standard unstructured labels. So with this, companies will basically, and research centers, will basically be able to have one model that will fit all the data they have, which is really interesting for their work. It provides a consistent and extensible work frame for building metadata, and it enables integration and querying of building data for analytics and control. So how brick entities work are, like you can see here, there is the equipment. So it's basically, we have entities and relationships between them. So if we have here an equipment, it feeds it is located in a location, and it points to a certain point, and it has measurements. So very simply put, that's what the ontology will look like. So the main issues that are solved with bricks are the semantic modeling of data. So we represent the buildings and their system using RDF. We standardize the metadata with predefined classes, and we facilitate data integration by combining data from disparate sources into a unified graph, and we allow linking of building components and energy data. And of course, the interoperability that we are focusing on because it allows you to work across platforms, and it is basically database independent, since we can model a lot of the databases and the data structures in it. Now, what does our own ontology look like? So we have this example of one building that we had, of one school. I am sorry, but I cannot read the name. I'm bad at Swedish. But you can see here, this is the building that is in Burio. And it has an activity type which is a skola or a sports center. It has an address that you can see there. It has a part in the energy usage, and it has a total energy consumption here in kilowatts. Same, it has the energy class, the floor area, and a year built. Of course, this is just an initial model of how to model this. There is many more relations that we can withdraw from this, but for our use case, we found that these are the most important ones. So now, how can we make advantage of this? Well, we make advantage of it with Sparkle. So Sparkle is an RDF query language that allows us to basically request data from this ontology. It enables us to have insights, for example, for the total energy consumption, the identifying of high energy systems, and it facilitates fault detection and energy optimization. So with this, coming back to this schema, it will easily show us the relationships between all the different entities and the different ways of how the information is structured. So with this, we have created an API, and we will summarize with this with Ken.
Okay, so to summarize what we did, with the amount of data that we generated from the smart buildings, which are the CSV files that we got, or that were given to us, they were like rich in variety. We have a lot of columns and a lot of data within it. And they were complicated to do data analysis and manipulation. The reason why is because they were unstructured. To solve this issue, we were able to do the ontology schema in order to visualize it better and to help afterwards to build the APIs in order to get specific data that we were looking for. In this way, we were able to standardize and organize the data even better for the smart buildings, and this ontology schema can further be used for a lot of smart buildings that are, for example, within Skellefteå commune. And to make it easier for the end user, we also built a website or like a UI where we put the results of our data visualizations. The user also can query the APIs, and we created the schema of our ontology there as well. So we're going to show the UI now. Okay, so this is our UI. We have a short explanation of what this UI does. For example, we go to the API calls, and this is going to lead the manipulation that we can do to get the to query, for example, something from our ontology schema. We have some ready calls that we can make. For example, get all buildings. If we click, we can get the building name and the address for each of the 4 buildings that we had in our schema. We can get the total energy usage. We query that, and we see the total energy usage per building. Activity types. Building conducted after 2000, for example, we put the year. If the year is 2000, it's going to give us the table with all the buildings built after the year 2000, which is only one. And the specific building, we can put here the name of the building that we want, and it's going to give us the corresponding energy consumption for it. We can also put interactive queries. We have a query that we can take, for example. We can put it here, and we just put run query, and it gives, for example, the building area of the corresponding building, also the address, We can also put other queries if we want to. So this is how this page works. Also, in the ontology schema, we can have a clearer view about it. We can see, for example, as Iman mentioned before, the building has floor and we have the corresponding values. Year built has part, energy class, for example, for this building is class C. So this is like the whole ontology schema that was built with the data set we were given, which is quite complicated, but it can be further extended if necessary by adding other buildings and other factors as well, columns that might affect the energy usage for the building. And also here we present some visualizations that we did and give some explanation, like for example, we have different type of visualization that we did. For example, we have the correlation matrix and we can see the relationship between, for example, energy consumption and, let's say, normalized energy. We can see that we have some correlations that are highly positively correlated and some others that are not really correlated. So it depends on the factors and data that we are comparing. And this is also the schema of the energy consumption compared to the building area, and we can see that buildings that are with like lower energy efficiency, consequently they consume more energy. And yeah, we have explanations for each case. So yeah, this is what we had, and okay, and regarding further developments, we can include also incorporation of natural language processing the model to automate tagging and classification, semantic understanding and entity solution, support complex queries, like even further the complex queries that we had in the website, and facilitating interoperability. And this is the presentation.
Do we have any questions? If not, thank you again.